been a good day. It's been a long day today. So we're going. I think what are we working on today? So today we're working on debugging a usage fault that we found. In fact, actually, the point of today isn't actually to debug this specific usage fault. Rather, the point of today is to sort of walk through how to fault in microcontrollers. Right now, I'll be talking about ARM and probably ARM v7 mostly, because that's what I have on my desk and that's what I'm using. So yeah, that's what we're using today, and that's what I found an error on. And you usually need one usually needs an actual error. Well, you can cause one and debug that one, but it's always awesome if you can find one in the wild and then find out if you can debug it and find out what happens to it. So basically, what we're going to be doing today is we're going to be going through a usage fault I found on one of the sample drivers that we checked out. So there's this sample, zephyer samples drivers I2S codec. And this sample has boards. This sample has a board definition for a board that I have, which is the STM32F4 Discovery 1. This one. Yeah. And that's the one I'll be using. So I'll be using this one. It's kind of hooked up and it's all on stuff and whatever. And basically, I think, if I remember correctly, whoever wrote this board overlay warned us that the board actually, this doesn't work. So, yeah, let's look at it. So even though the STM32F4 board overlay is tuned for 22 or 44 or 22,500 or 44,100 or 88,200 kilohertz audio output, it doesn't have enough RAM to hold all the buffers allocated by this sample at such high audio rates. So I think that's why the writer here actually reduces the sample frequency to 8,000. Remember the other day we were working on a I2S codec and we said that we're getting 44,100 samples, 44,100 hertz in samples. So that means we're getting 44,100 samples every second. So I think the attempt here was to reduce the sampling to 8,000. So we get 8,000 every second, and then we just enabled an audio codec. And then along with that, there is some overlay here, and I think if I'm right, this just enables the I2S codecs TX. Why is this just a transfer? Isn't this code supposed to do both? Let's look. This sample demonstrates how to use an I2S driver in a simple processing of an audio stream. It configures and starts from memory buffer, a sample sine wave, or from a DMIC, DMic, digital mic, which actually the board also has, if I'm not wrong. So let's quickly look at the schematics of this board, and then before we go on. So this board does have, I want to look at, I should look at wake sources, but that's for later. So if you see here, I think this is the audio codec, and then I'm going to reduce this to 100 so we can see everything. So it looks like this is the audio codec. It does have an audio codec, I2C address 0x94, and the CS4 3L22 new. Perhaps let's go find out what that is. I expect this is a audio codec that we can use. So what is that? What is that? What is that? What is that? This should be some sort of audio codec. It's a low power digital analog headphone class D speaker amplifier. Okay, cool. So that's going to be this part of the board, basically. Have this headphone driver over here. So it's going to be somewhere here. And I think if you do look actually closely, this is the chip that they're mentioning. This chip over here. So cool. So basically what I'm trying to show is that this board has an audio codec, and I believe, yes, this should be a microphone. I believe this is a ST-MEMS microphone. Yeah, MEMS audio sensor, omnidirectional. This is the same thing as the other board that we're using, which has the other MEMS microphone. So basically what I'm saying is this board does have an audio codec on it, and it also has a microphone on it. Those are the two things I'm saying now. Okay, cool. So this just does what? What does this do? Let's look at it again. This sample demonstrates how to use an I2S driver in simple processing of an audio stream. It configures and starts from memory, from a memory buffer, a sample sine wave, or from a digital mic to record I2S and send that codec to, and send I2S data to codec, to the codec. So I'm assuming it just said, it records, so let's look at that sample again. It records here from this microphone, which is PDM, and then I think this is PDM connected to the I2S peripheral, and then from the I2S peripheral this will connect into this audio codec, and then from the audio codec you can either consume that data internally, or you can send it out to the headphones and do something with them. Basically, is what happens. So this is the setup of this board, but that's what this code does. So let's quickly build out this code and try it out, and then see what happens. Okay, cool. So this is what happens, but I'll do a Control AK, yes, and then I'll let that be there, and then I'll come back, and then I will do SKQ. Oh, yeah, cool. So let's build up this code and see what happens. So it's west build -b STM32F4 Disco. Let's do an always. So let's do a fresh build as always. If anyone has any questions already, feel free to throw them my way, please. Okay, while that's building. Okay. Cool. Let's see. That's building. Cool, amazing. It did build. So let's do west flash -r open OCD. That should be okay. That should flash everything. We should get it. It's on the board. That's cool. So now let's go back here and let's do some, let's actually scan what is happening on the board. There's nothing that's happening. So what I'm going to do here is I'm going to press the reset button. I think that's the black button on the side. Yep. And then that will reboot it, and exactly. So now we have what I was looking at before. So codec sample, start stream, UsageFault, illegal use of EPSR, and then we have register 1 all the way to 15, I think, and then we have the value of the XPSR register. And then faulting instruction R15, program counter is 0. It shouldn't be 0. We shall discover why right now. So before we actually jump into this, because it's quite it's almost straightforward to go to where this is if you have enough background information. So before we actually jump into this, let's actually look at let's look at the faults that are offered in Zephyr for us, and then we can kind of sort of build up from there. I think I have an open window somewhere here, and then I should have Zephyr faults. I'm just gonna Zephyr faults, I think. Yeah, fatal errors in Zephyr. Cool. This is basically what we have, and then I'm gonna go to my notes, which I shall share. They will be in the link, and they should be somewhere. So let's go through my notes quickly. And this is basically a summary of what I've read from the link that I've shown before. So Zephyr gives us a mechanism of inducing or causing fatal errors from the application and from the kernel. And we have a few of this mechanism. So let's go through a few of them. So we have, basically we can induce runtime assertions. And these are assertions that we can check some sort of condition in runtime. And if that condition is not met, we can basically do, we can use an assert to check that condition. And if that condition is not met, we can basically cause a fatal error. We can make the app crash, is basically what we're saying. And then also, in the event of this happening, we can also use a assert post action, which is a callback that we can use to handle this sort of faults. Okay. And then the next one which I feel like I like more than the other one is build assert, which is for build time assertion. So this is all information that I'm getting from here. Build assert here. So this is the same as the assertion that we just covered, just that this one is run at build time. And when this assertion is run at build time, if your condition is not met, then this will cause the compiler to generate a fatal error, and this will cause your compiler to fail. I like this one better. If you have access to the condition or the condition that you're checking during compile time, I guess that I feel like this brings the discovery of errors closer to the development. And if you're getting assertion errors when you're doing the building, it's much better than if you're trying to debug assertion errors that have already reached an end user somewhere. I think that's easier, and I feel much better about this. And I feel like I should use this more in order to cover all my cases, rather than using the usual assert. But in some cases, you will not have access to this, and you do want the thing to fail, or rather to reset, to go back to reset if you have that kind of data, and you end up with the assert. You could even end up using both, if I'm not wrong. Okay, cool. And then Zephyr also provides us a kernel oops. This is a software triggered fatal error caused by a k-oops function. And this should be, one can invoke this. It's a k-oops. It's like ksem or k mutex. It's a kernel object. It's in the kernel. If you're using Zephyr, you have access to this function, and you can just type it out and it should work out. Basically, I'm not going to go back and do that. I'll stay here. And then we also have a kernel panic, which is sort of like kernel oops in the way I see it, but it's used to indicate that something in the kernel has gone or rather some state that is unrecoverable has been reached by the kernel. You could use this probably in your drivers and stuff, or if you're implementing subsystems of some sort, maybe not drivers, and then you have some state that a subsystem can't reach that should not be reached. I see where you can use a panic like this. And I think from what I'm seeing is Zephyr tries to differentiate between kernel fails and userland fails, and then gives you different amenities to handle both of them. Okay, cool. And then after kernel panic, we also have spurious interrupts. So these are interrupts that are caused, but the kernel doesn't know how to handle them. Say your kernel's just going on with its own thing, and then it doesn't use, say, GPIO bank A or port A, and then suddenly it gets an interrupt for GPIO port A, which is not configured, or it might even be configured, but the kernel has not been given a handler for that interrupt. So that will cause kernel error, spurious interrupt error, interrupt request error, and this is also a fatal error. This fatal errors is when your app will stop. It won't log, it won't do something. This is an error. You basically reach an unrecoverable state. So you can't go backwards. Some of them can be recovered. Discovered. You can, if you do the handler right, you might be able to recover them. But from what I can see, you can't go backwards. Okay, and you necessarily don't want to. It depends. It always depends. You might not want to, but you might be in a place where this thread is the one that's erroring out, but you don't want everything else to error out. So you basically might not want to go back to reset, but do some sort of in-house handling of the thread or such. That becomes an implementation detail, so we won't cover it here. And then, as usual, which I suspect is the thing that we're going to be facing here, is stack overflows. Whenever you have a thread and the thread has an assigned amount of stack, like our audio app, GitHub, or rather our BLE apps, should I call it, the BLE app I've been working on. So if you see our threads, whenever we make our threads, whenever we construct our threads here, we give them a stack size, and my stack sizes are just 1024 bytes, I guess. If your thread does something like using more stack or writing to more stack than it has been given, this will cause something called a stack overflow. So stack overflow isn't just a website, but it's an actual thing that could happen. It's basically your stack of plates going too high and falling on the side. Think about it that way. It's the same as the stack overflow logo. So think about a growing tower of plates, and then it grows too long, and then it becomes unstable and falls to the side. That's a stack overflow, basically. So that can cause an unrecoverable error. Let's go back to the easier to read one, not my notes. Cool. So, and then there's a few ways stack overflows can be combated or can be dealt with. And then there's also a few ways that you're allowed to do stuff with stack overflows. So if a thread is running in user mode and it overflows the stack, it can cause a not fatal error, but it won't be allowed to write to a JSON memory. So basically it won't be allowed to corrupt the neighbor's memory. That's what will happen. But then this error will be reported, and it might even be fatal, but you might be able to do some sort of in-house handling. And then the next point is you can have some sort of hardware protection. If your implementation of the ARM microcontroller, basically if your manufacturer provides a memory protection unit, you could use configure hardware stack protection, and I think this let's actually go to that. So I think this hardware stack protection. Select this option to enable the hardware-based platform features to catch stack overflows when the system is running in privilege mode. So you can use this for threads that are not in user mode. Threads that are like in supervisor mode or in OS mode or in kernel mode, however way you call them. And then we also have some more. I'm rushing through this because this is just building up data that we need to go on for the next thing. We do have some guardrails in place, and if you don't have a hardware memory protection unit or memory management unit, you can use Stack Sentinel, And Stack Sentinel is basically a software-only Stack Overflow detection feature. The problem, or rather the thing that makes the Stack Sentinel not ideal, or not ideal in some ways, is that it's run periodically. So think about it being run maybe once every second or something of sort. Second is long. Let's think about maybe 500 milliseconds, but run periodically. When it's being run periodically, a Stack Overflow may occur between the runs. So run 1 and then run 2 and then a Stack Overflow happens in the middle. It will detect that a Stack Overflow has happened, but it cannot guarantee memory protection or memory. It can't guarantee that your memory will still be okay because it's run periodically, and it's also a software only thing. So it's not there watching the memory all the time and then so on and so forth, if I can say. And then finally, we have something called stack canaries. This is, man, it's a canary in a gold mine. The same reason you take a canary in a gold mine. Why do you take a canary in a gold mine? I hope everyone knows about this. So there's something called canary. I don't know how to say that word. Canary in a gold mine. It's a little yellow bird. It doesn't even matter. In a coal mine. So, in a coal mine. Okay, cool. So, you take before, I don't know if it's true, but the story goes that let's see how they say it.
Canary in a coal mine.
Canary in a coal mine. Let's see the general.
Canary in a coal mine.
It's cool. You can say it anyways. But the story here is that before we had gas detectors, miners would carry a little bird into the mines, because some mines can contain poisonous gases, and the poisonous gases would kill the bird. Yeah, I know, animal abuse, but the poisonous gases would kill the birds, and if the bird would die, the miners would have to get out quickly. Just because now you're walking in these dark tunnels underground, and you don't know if there's you cannot detect poison. If you were in a room full of carbon monoxide, that is just silent execution, because you wouldn't even know you're dying, because it's actually quite ugly, because you're breathing, you would just keep breathing air, but you'd still be suffocating, and then or nitrogen or something of the sort. But the point is, when miners would go into coal mines in the old times, they would go with a little bird in a box, and if the bird died, they would run out. So you can do the same thing in your memory with Zephyr. You can put canaries in places in your memory to mark that these places should not be crossed, and if those canaries get overwritten, you know that your stack has been corrupted, and you stop execution or you cause a fatal error. Basically, these are the ways Zephyr allows us as application developers and kernel developers to cause faults or faults. And it's good to know, it's good to be aware about this, so that when you're looking at something like this, you already have an idea of like, what am I looking at? Where could it be happening? Why is it happening? Before you even just try and fix it, it's good to always know how these things happen. That way you build the intuition of knowing where to go check, because sometimes the error could be like, this is probably a Stack Overflow because we don't have enough RAM on the device. We were checking RAM the other day, and this thing has like maybe 150 KB or something, 192 KB or something of RAM, kilobytes, and your computer or your phone probably has like 10 GB or something. It's amazing. But here's the thing. So this is probably going to be either a null pointer or something of the sort, and you'll see the reason we know that. We don't even actually that's actually quite a good thing. We don't even have to go into the code to learn what this error is and how to debug kind of this kind of error. Once you know how to do that, it's very easy to hear what the error is or to look at the error and start building up from there. Okay, so what we just did, the first section of this was covering how Zephyr allows us to raise these errors. Okay, in the second part of this video, which is in a minute or so, I'm going to check the ARM reference manual. And in the ARM reference manual, we can look at faults. And for now, we're going to look at usage faults. And then we can kind of build some intuition of why they happen, where they happen, and then it becomes quite easy to start looking at this. Anyways, before I jump onto that, does anyone have any questions? Please point them up on Discord or on WhatsApp or on the YouTube comments before I go on. Cool. No questions so far? Amazing. Oh, maybe I'm lagging. So whenever you get that, if you have a question, please do ask. Let me go to the next thing. So we found out how we can induce or cause fatal errors. So now let's actually look at the next part of this. Let's go find the ARM v7 reference manual. So cool. ARM v7 reference manual. It's funny because once you start debugging things like this, you end up in a place where it's v7. You end up in a place where you start understanding and then it's also ARM v7 reference line. You start understanding how the operating system implements stuff, and you start actually walking through assembly in some sort of weird way. So it's very educating to start building your intuition for things like this. So we have this manual. Okay, we have this manual. It's an ARM v7 architecture reference manual, and in this manual I can do something like Control F, usage fault. No, not that one. I want like the topic on the usage fault. Amazing. So it's here, and I think I have a better one on my machine, so we can look at it. I bet you I have a bigger one on my machine. So same document, just bigger font, so we can look at it. And as you can see, I was studying before. Usage fault. So basically, I just want this one here. Aha, let's read this. So we have a usage fault, and I will remove this so that we can read it. Usage fault. The usage fault handles non-memory related faults caused by instruction execution. A number of different situations cause usage faults, including undefined instructions, invalid state on instruction execution, error on exception return, attempt to access a disabled or an unavailable core processor, and then the other following can also cause it: a word or a half word memory access to an unaligned memory address, and division by 0. So most of these are easy. Undefined instruction. You try to do something this processor does not know how to do. Cool. Invalid state on instruction execution. This is actually kind of the one that is happening right now, but you have something called a T-bit, and that instructs our architecture on how to, which is a thumb architecture. So it tells the thumb architecture some state has to be held in a certain way, and if that state is not held in that way, it just explodes. Error on exception return. So you have you return an exception, you get an error, usage fault. And then attempt to access a disabled or unavailable core processor. You are trying to use floating point units, and you don't have floating point units. Boom, You're trying to use a cryptographic engine. You don't have a cryptographic engine. Boom, something of the sort. Okay. A word or half word memory access to an aligned address. So if you guys remember if you guys and girls, if everyone remembers when we were debugging our memory slab issues in Zephyr, we would arrange our data in something like 4 bytes, if I remember well. So there's this. Let's look at the pull request. So I'm jumping through many code bases to show you this, so that we can actually have some sense. If you remember here, some files change, and I think it's going to be the audio service file that we're going to look at. We made a mem slab, or actually audio services. We made we arranged data in bytes per sample size of int32. So that's 4 bytes, 4 bytes per sample. So you have like data arranged in basically units that the CPU can understand. And you have like here we have 4 bytes, which is 8-bit, 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 8-bit. If you try to do something like access the 5th bit as the next packet that you are going to consume, the processor would go like, wait, that's not divisible by the thing that we do, which means that is an unaligned data. And when you try and access that, the processor is going to throw back a usage fault at you and say like, oh no, you're trying to use this data or this container in a way that it's not supposed to use it, and that will cause a usage fault. Cool. So let's go back here. And then division by 0. Yeah, I know. What is 2 divided by 0? That's a good question for someday. But if you divide by 0, it literally is undefined. We don't know what happens when you divide by 0. It's not like divide by 1, it doesn't split, or divide by 2, it splits by 2. What happens when you divide by 0? We do not know. So that is undefined. So that is a usage fault. Okay, cool. So that's going to be in my notes somewhere here, which I'm going to upload. So we basically found out why usage faults can happen. So let's go find, before we go on. So before we go on, let's look at the thing. There was some note. Okay, so software can disable this fault, and if it does, a usage fault escalates into a hard fault. And then you can also put priorities in which fault to handle first. And faults they're documented. So a hard fault is the generic fault. I'm not gonna go. I promise to do usage faults, and I'm trying not to jump out and to do something else. So let's go and look at our error again. Okay, so we know we have a usage fault. Cool. We know what usage faults are. So now we get the next line, and it says, we know we have a usage fault, and we get the next line, and it says illegal use of the EPSR. What's the EPSR? Let's find it. EPSR. You could start, ideally, you could even start like this. So you've never encountered this before. So EPSR, ARM. Status register. Cool. So this is, cool. So something like that. You see, if you build up slowly, if you just go finding the next breadcrumb, you can build up slowly to what the thing is, what the problem is. But since we now know what an EPSR is, we can go back to our reference manual so that we can look at it. EPSR, isn't it? I believe so. And you're going to be some sort of status register. What is EPSR? Let's find EPSR. Valid EPSR? No. EPSR? No, that's not the one I'm looking for. The EPSR page? Maybe that one? No. Can I go there? Let's look at it. So these are all status registers. Let's go look at what the special purpose program registers XPSR. So XPSR could be APSR, IPSR, EPSR. They could all be whatever. So they're all special purpose registers. Special purpose registers. Okay, cool. So let's look at APSR. Aha, now we get into here. So this now starts being a bit clearer. The EPSR contains the T bit that is set to 1 to indicate that the processor executes thumb instructions. I mean, we have Google. Let's find out what this thing is. So what is a thumb instruction? ARM thumb instruction. That's full of typos, but it doesn't matter. Yeah, ARM thumb. So there you go. The ARM processor has 2 instruction sets. So instruction sets is the assembly that you're allowed to write for your processor. That's okay? That's cool. So it has 2 instruction sets, and you can use whichever one is applicable to the processor you're using at the moment. So I think it's thumb V1 and thumb V2, something of the sort, but it's fine. I'm not so sure. EPSR contains a T bit. Well, that is set. Let's look at how that thing is set. So this is the EPSR register, I think, EPSR, IPSR, APSR, and the bit they're talking about is T bit, this one. Reserved if the DSP is reserved if the DSP extension is not implemented. I want to know which one that is. So this one, GE. Okay, cool. But we'll get to that one when we do the DSP. But the EPSR contains a T bit that is set to 1 to indicate that the processor executes thumb instructions, and an overlaid ICI or IT field that supports interrupt, continue, load, store instructions in the IT instruction, interrupt instruction. So the ARM A and R architecture profiles have 2 alternatives instruction sets, ARM and thumb. The instruction set state identifies the current instruction set, and the PSR T bit identifies that state. So the PSR T bit, the special purpose register T bit, I'm assuming all of them have a T bit. T bit, I guess this whole thing is combined as one register. So the PSR T bit identifies that state. The M profile supports only the thumb instruction set, and therefore the processor can execute instructions only if the T bit is set to 1. What is this saying? In that register, if that bit or if that register bank is not set to 1, then this processor is not allowed to execute that instruction set. That's a rule from ARM themselves. Okay? All fields are read as 0 during an MRS instruction, and the processor ignores writes to the EPSR by an MSR instruction. MSR, MRS, M set register, M reset register, something of the sort. I need to look at those 2, but I'm just seeing if I'm guessing right now. So the EPSR T bit supports the ARM architecture into working model. However, as ARM v7 only supports execution of thumb instructions, it must always be maintained with the value 1. Okay? Updates to the PC is, and I'll cheat here by explaining something I have not shown. The PC is a program counter. So this is a register that holds the current execution. The current execution holds the address of the current instruction plus 8 bytes. So this is a register that just holds the address of the current instruction. You're doing an addition. The pointer to the addition is going to be in the program counter. Make sense? You're doing a move. The pointer to move is going to be in the PC. So updates to the PC that comply with the thumb instruction and interworking rules must update the EPSR.T accordingly. Instruction execution with the EPSR.T set to 0 causes the invalid state usage fault. In state, a reset. Okay? So, what did we just learn? We have an EPSR register. If the EPSR register has a bit, let's say it this way. If the EPSR T register is set to 0, this causes an invalid usage fault by causing an invalid state. And the EPSR T bit is updated with every instruction. So whenever you run an instruction, you will generate some metadata, and that metadata is going to be used to update the T bit. If that T bit is ever set to 0, this causes an invalid state or a usage fault. Make sense? So let's actually go back to our error and see if we can make any sense of it. So we know illegal use of the EPSR. Already we know. Already this is telling us what has happened. And then it shows us R0, R1, R2, R3, R12, R14. These are the registers we used. And then it's showing us the XPSR register. So remember EPSR. And then we want to come back and go like, let's count some bits. So there's 0 to 32. Do you remember how we did this with 0 to 32? So 0 to 32 is going to be 16 of them, because each one of them is going to be each two. So we had a 24-bit packed in a 32-bit, and the last two were the 8 bits that we were not using. So if we have 32 bits, then we have 16 of them. 16 cross X4. How did we explain that in the last blog? Let's do dioges. Jump backwards and forwards when you're learning a lot. It helps. Yes, true. So we had cross 1 2 3 4 5 6 0 0. Yeah. So look, we have 24-bit audio, 8-bit packing. So that means if we're looking at cross, yeah. So this is 1 2 3 4 5 1 2 3 4 5 6 7 8. So each one of them, 32 divided by 8. 32 divided by 8. 32 divided by 8. Is it even divisible? 32 divided by 8. It's 4. So each one of them is 4 bits. Each one of them is a half word, I think. Half word or a byte. I don't know. So basically what I'm saying is we can count through here. So remember what we need to look at is here. So this is 0 up to 8, and then 8 to like 10, and then to 15, and then to 19, and then to 23. What does that mean? We need 2 on this side. So let's 2 on this side, because this is kind of opposite the one that we were using for. Remember, we were using left aligned data. This is kind of right aligned, so it doesn't matter. So, but what I'm trying to show is this is the 23rd. Yeah, this is the 23rd bit. 23rd from least significant, from LSB. So if we go, so basically there's 2 digits and then the T. Okay, 2 digits and then the T. So let's look at our error. 2 digits and then the T. Let's look at our error. 0 cross 2 0. This should never. The 3rd digit is 0. And what does that tell us? We did some sort of instruction that updated the program counter to 0, and that caused the T bit to be reset. And actually, you can see here, faulting instruction address R15 program counter has been set to 0. When program counter gets set to 0, we have an invalid state. I wonder if anyone has any questions so far. Do you see how we sort of built up all the way? We used all of this documentation to find out what the things that we were looking at are. And then once we found that out, we can now start actually walking through this error and trying to see it. Because now, basically, we've not even opened the code. We have just looked at a few reference manuals and understood the error that is in front of us. And we have an idea of what is causing the error. Most likely, this is going to be, if we look at our notes, it's going to be something like an undefined, some sort of undefined error. Or it could be that we're attempting to access some stack that we can't use. So we basically had like some sort of stack overflow or something is null. That's usually the two cases. We're pointing at the wrong address, or we are pointing at something that is null and it's supposed to be not null. I'll pause a bit so we can do questions. And anyways, I'm almost at an hour. Yeah, so any question? No, it's not. It's not a pre-recorded stream, Marvin. No, this is C, not C++. I promise you it's not a pre-recorded stream. I wish I was that confident and I could pre-record streams, but I actually do like doing things live. It works so very well for me. I learn a lot, I get to remember a lot, and I get to do a lot with people and a lot of times to talk with people. So it's not a pre-recorded stream. Okay. Yeah. I said your name in the stream, so it's not. It's definitely not pre-recorded. Okay, so we've walked through all of this intuition on how to build up information that we are going to use to debug this error that is happening. Yeah, and we basically have all of the building blocks that we can use to analyze this error. The good thing is, and this will be in my notes later, I actually have thought about doing pre-recorded streams because it's really hard. It's very taxing to do a stream almost every day. Okay, so it's very taxing. So there is amenities in Zephyr that we can use to sort of there are amenities in Zephyr that we can use to collect and basically reuse information. No. I'm distracted. Zephyr provides us with amenities that we can dig into broken code. Okay. However, it's not just in Zephyr. You can use a GDB stub in Zephyr, and Zephyr will do something like load into GDB for you, and then you can, from there on, you can kind of debug. Let's quickly look at those. All of this will be in my blog. It's almost an hour. It's kind of much later than I usually do my streams, so I apologize about that. But it's almost been an hour. I don't want to make this last too long because the second part of this, now actually digging into this, could take a long time. But what Zephyr allows us to do is dig into, basically walk all the way to where that function is. So we can walk all the way to, this is the calling register. Okay, so the LR is a calling register, if I am right. LR. So the LR R14 sometimes can be referred link register, used to store the return link. So this it can enable us to walk all the way to the function that called this, and then we can look at what it is. But we also have a few hints, because if we look at it, if we look at this error, there's a log here. It says start stream, and then that's going to be it. So if we go into our code and look for that start stream, where is this? And then so ps start stream. I feel like it's in the codec, so let's look at the codec. Start streams. Yeah, for here. So you see, start stream, and then something in here is going to cause the memory error. And the thing we can't do is we can't use Control-Shift-T. I want to do that, and then I want to do something like this. We can't use ARM. We can't use some amenities by ARM. Basically, ARM none this, and it will basically take us to the error. And this, I can copy this. And if you see, I'm pointing it at the instruction that caused the error. So the return to that instruction. Okay, cool. So let's look at the error again so that we have it. That I'm pointing at this. So we want to know who calls this return address. Let's go to the return address. So who called this so that an error can happen? So let's go there. Okay. And what we can do is we can use this line of code in our thing, and that can I want somewhere with env, I think. Control R, activate. Cool. So if we do that and we post this here, that was something else. So I want to go back to my notes. If we do that and we copy this, Control Shift V, Control V. Is this copyable? Oh, okay. Sorry. Because we're in insert mode, we can't copy. Cool. Control V, Control Shift V. Okay, cool. I'll do that. I'll remove that, and then I will remove this. And this won't work because this is in the wrong place. So you want something like build zephyer that. Okay. Before I know it's worked, I know it's did the magic, but let's actually just look at what ls build zephyer. So we want to go through this, which is an executable and link format, to tell us what is happening. So basically I squared s common c. I squared s common c. So the error is happening in zephyer, which we can't actually look at from GitHub. I can look at it on my computer, but I don't want to. We can always just take clear. We can also just take so we can do this and less that copy less man less. Let's nvim it so we just know that we can Control Shift V. I don't want the line number. Let's open that. Delete the swap thing. I2S common. Why do I have I debugged this before? I think it was line number 37. I think I've debugged this before. Okay. what? I2S common. No, I'll just leave that file alone. Let's go and look at it from. Let us go and look at it from the browser actually. Therefore. Okay, cool. I'm almost done. So let's just find out the line and then we can stop it there. So it's in the I2S. Let's look at clear. So basically this pointed us to where. What did we use here? Can we man rm non ebi dash order to line? Can we man that? Yeah. Convert addresses or symbol offset into file names and line numbers. So you can give this your elf executable or your a.out, and it will give you the line and file name that is represented by the memory address that you're looking at. Okay, so it's I2S common.c. I2S common.c 37. So in drivers I2S. Drivers I2S common line number 37. Line number 37. It's gonna be some memory access of some sort. If not txconfig, return IO. If not txconfig. So this is failing. Wow. I'm actually quite impressed. We found out that it's a different error. So this is failing because txconfig is exploding. Because txconfig, because actual, so it's if it's pointing at 37, it means 36 is the issue, because what it's telling us is that I2S config get the I2S direction tx fails. That's odd, because I think our app does do that. Do we have something that is open? Actually, I just want to open that. So we do have project config I2S pygmy, and then let's look at the boards, and then if we look at the overlay, we do have a TX I2S codec TX I2S3. And that is where that thing is connected, because remember our schematic. Remember our schematic and where the I2S. This is connected. This indeed, or is this? This indeed is connected to PC3 and PB10, which I think all go to. Go to page 10. PC3 and PB10. PC3 and PB10. Audio. PC3 and PB10. PC3 and PB10. I don't want to go to. Yo, that's so cool. You can. Oh my god. Schematic's cool. You can click on a pin and that's so cool. That is so cool. PC3 and PB10. PC3 and PB10. So I2S3. I2S3. I want to look at the pinout. I want to look at the pinout of STM32F4. Is it you? Is there a pinout in here? Pinout? Is there hardware lab? Pinout. No. I think I better find this online. Let's do. So we're looking for PB10, PC3, and PC4. What are those connected to? because I suspect they're connected to this. STM32F4 Discovery pin out. Yeah, this is my favorite link. My favorite link here. So what are we looking at? What are we looking for? PC3 and PC4 and PB10. So PB10, PC3. So B10, 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 not here. B10, 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 B10. Oh, mic. B10 goes to the mic. And then I think, and it also goes to I2C SCL, but so PC3 and PC4, where do they go? PC3 and PC4, PC3, C3, 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 C3 and C4, C6, C3 and C4, C3 and C4. C3 goes to mic, C4 goes where? I cannot see C4 quite availably. I don't think C4 is exposed. C4 goes to the ADC. So that's some sort of converter that takes data from the mic into the codec. But basically what we've discovered is somewhere along the line, the setting up of the I2S codec fails. Yeah, fails because so let's look at another one. So let's look at this overlay. Let's look at some other overlay. Let's look at here. But let's look at the main. What does the main do? What does the main want? I2 codecs DX. That's the one we're looking for. And it is set up. It is set up. I mean, cut build zephyer.config, and then this in this grep I2S 2S. Yeah, config DT has I2S enabled, PLL I2S enabled, I2S yes, init priority dot. Yeah, it's enabled. And then let's go cut. Let's actually look at the DTS that is provided. Zephyer.dts grep I2S I2S3 A10. I2S3, this is compatible, yes. Address cells, yes. Are we staying a status okay? Status is okay. Pins is going to there and there, but this is from STM32, from this file, STM32F4, STM32, so boards Zephyer boards STM32F4, STM32F4 Disco DTS 206. So let's go to that file. Let's go to that file. So boards ST 206 ST DTS. My little workhorse STM32F4 Disco. ST makes a lot of boards. STM32F4 Disco. STM32F4 Disco. Disco, and then it wants us to go to line 206. Line 206. L206. Yeah. And this is I2S3, and we can see, so clocks are set up there, and let's see the pins. I2S3 PA4, I2SC PC10, I2C, PC12, PC7. So it is enabled. I mean, how do I say this? It is enabled. PF4. These are probably the wires into the audio codec. PF4, PC12. Yeah, let's look at them. PF4, PC12, PC10, PD4, PC7. Okay, so the PF4, PC10, PC10, PC12. Yes, it's there. PD4 is not there. Okay, PD4 is not there. And PC7 is there. But what I need to discover is, what does this audio codec do with PC4? Isn't it? Isn't it? Isn't it? Is that the one you want to see? Which one is missing? PD4 is missing here. PD4 is missing. I want to see, where does PD4 go? Yeah, let's go to, I think here. PD4. PD4 goes to audio reset. So it's just a reset pin and it's not being used. This could be why it's failing. This could be why it's failing. Because without a reset pin, without a reset pin, this might not work. It depends on this codec. So I need, now you see, now we start debugging this codec, because we need to find out, does this codec like the PD4 need or like the PD4 button or not? That's kind of what we need to find out here. But anyways, we're going on past an hour now, and I think I'm going to stop there now. My blog here, let's actually finish my blog, or rather not my blog, my notes for this. That gives you all of that, all of this inside. Git status 2025-09, yeah. Git commit -m add debugging UsageFault notes. I'm gonna git push. I'll wait for that to come up so that we can put it in the cart 2025-09 dash top dash 9 top dash 3 top. Cut this here. So let's find this. Let's go here, edit. Say one runs into some sort of fault, e.g. HardFault or UsageFault. How do we build the intuition to debug and dig through these sorts of faults? Join me as I dig through to the source of our fault that I found in the Zephyr codebase. The codebase on my STM32F4 Discovery 1 board. Yeah, so, and then notes and links. Let's add the link to the notes. if you have any questions, this is me closing up. So if you have any questions, please do ask them now, and I should be able to answer some. Let's look at it here. So notes and links. Here's the notes. These are the notes from today. These are the notes from today. So look at them. Follow the video. You should be able to. You should actually be able to get that file and go do the stuff I've done. So, and it should be okay. You might not actually get the error itself because you would need the board, but if you just the code we're working on now is actually not that, but is this I2S codec, I2S driver. I think it's somewhere here. No, not even that. Not even that. It's in samples, drivers, samples, drivers, I2S, I2S. This is me closing up. So if you have any questions, please throw them on the chat right now. I2S codec. This is it. This is the code that we're working on. I don't think we need the BLE format in here today because we're not working on that. Cool. And then hardware and setup. I think today we are working on the STM32F4 Disco. So let me change that. STM32F4 Disco zephyer. Might as well just link it to this one properly. So here's the file that we're working on today, and hardware we're working on here. Cool. Okay. Notes up there. Yeah. And as always, remember to try and fix things that exist rather than try and succumb to the not invented here thing. You don't have to build everything. There's a lot of awesome stuff out there you can go find out and get involved in. And if that's difficult for you, send me a message or join one of the groups and we should be able to talk you through this. But overall, all in all, thank you all so much for joining me for this last hour. It was a really difficult one to get to today, but we did, and I think that was awesome. We've gone through how to... What I'm doing is walking through these things in the open in the hopes that I can share the sort of information I was looking for when I was learning this. So I don't know if this was productive for you or not, but we definitely walked through how to look at an error that is happening. Faults are usually mysterious errors, and to try and start breaking it down until it becomes something that we can follow through all the way to the code and do that. And you can do this with other programs. They don't have to be embedded programs. They don't have to be C programs. You could take the concept from here and go and apply them very successfully somewhere else, and you should be able to get similar results or better. In any case, thank you so much for joining me today. That was amazing. Cheers, and I will try and do another one probably tomorrow, probably in the morning, and we'll see where we go. Thank you so much. See you again, and that was awesome hanging today. Cheers. I'm closing up in case you're hanging out still. And I'm gonna end that stream now. I wonder if